Good evening. My name is Alfio Quarterone. I'm going to chair this last session. So the first speaker is Professor Will Schilders from TU Eindhoven. Will is also the president of ICIAM. And he is going to talk about the role of mathematics for the sustainable goals of UNESCO.
Okay, thank you very much, Alfio, and thank you for the organizers for giving me the opportunity to talk here about the role of mathematics for sustainability, and specifically for the sustainable goals of UNESCO. I will briefly go into the general role of mathematics and show some unexpected results, I think, and then I will go into mathematics and sustainability. So about the importance of mathematics. The work of mathematicians may not always be very transparent, and it looks like we are performing some miracles, but this is of course not true. It's just work, and it's present everywhere in mathematics. So you see many applications here, and behind each of these applications is mathematics, as you can see. And what I always said is mathematics gives an invisible contribution to visible successes. The role of mathematics, we live in a very dynamic world where mathematics is present everywhere, and this was very nicely expressed by a colleague of mine from Amsterdam, the CWI, Lex Schrijver. He said that he compared mathematics with oxygen. You take no notice of it when it's there. If it wasn't, you realize that you cannot do without it. So I think this is a very strong statement describing the role of mathematics. And mathematics also plays a big role in simulations. So besides experiment and theory, now we do a lot of simulations, so that's the third discipline. And mathematics plays a crucial role in computational science and engineering. Designing is done behind the screen nowadays, virtual design environments everywhere. And digital twinning in industry, artificial intelligence, and many more things. There's mathematics needed to do these things. And there is more, and as I said, I wanted to share some unexpected things with you. Everybody knows Moore's law, that computers and chips become faster every 2 years. What people don't know is that in simulations, mathematics play a decisive role, and they are outperforming the hardware improvements. And in fact, I always use this picture that's on the far side, on the right. People talk about software and hardware usually, but I like to talk also about the mathware so that we know where the mathematics is. And as you can see, here is 4 different methods that are used in simulations. And you see the improvement in the hardware, but also the improvement in the mathematics. And you see that the mathematics is indeed outperforming. And of course, it's a combined effect. You have to multiply the 2 numbers in order to get the advantage. And that's very apparent for this mixed integer programming that we see. 25 years ago, simulation would take 180 years. Now you can do that in 1 second. But if you would only rely on the computer speed up, then it would take still 10 days. So mathematics really helps here. And there's a mathematician from Belgium, Philippe Troin, who said that I would rather use today's algorithms on yesterday's computers than vice versa. And what I usually say is that if we rely only on the improvements in the hardware, we would now be doing the simulations of the 1990s. So it's very important. There's another thing, and that's the last thing I want to say about the mathematics. There's also a relation between mathematical ability and country competitiveness. So also in that respect, mathematics is very important. Okay, but this meeting is about sustainability, and I would like to concentrate now on mathematics and sustainability. The ISC was already mentioned this morning by Professor Pombero, and it's the International Science Council, and they do many things for sustainability. We are actually, ICIAM is a full member of the ISC, and 2 years ago the ISC had an International Year of Basic Sciences for Sustainable Development. And as Professor Pombero said this morning, now they have the International Decade of Basic Sciences for Sustainable Development. And I think that's a very important initiative where all the sciences work together. And indeed, it's high time that we do something. Yeah? Today's world faces many complex and interconnected challenges. There are many issues: food insecurity, inequality, land degradation, biodiversity loss, political unrest, and many more. And these are obstacles to development. So they put societies really at risk on a worldwide basis. And also the projected population growth in certain countries and climate change impacts will intensify these challenges. So mathematics is really trying to empower this sustainable development. It is fundamental on how we understand nature and also the uncertainties that are associated with that. For example, the COVID-19 pandemic, many governments were relying on mathematics to do predictions and also to understand social issues like vaccine hesitancy. Mathematics has also allowed for pivotal improvements in weather prediction. 41% of the global population is at risk from tropical cyclone flooding. And with new mathematical approaches, we can much better predict the path and the impact of cyclones. I will come back to that in a minute. Now, for about 10 years ago, 11 years ago, there was another initiative already by the mathematicians, Mathematics of Planet Earth, a worldwide initiative, and run by a mathematician in Montreal. So it was a year-long worldwide initiative with many different activities. And it grew into a real partnership of more than 150 scientific societies and research institutes, etc. So this initiative, MPE 2013, underscored the multidisciplinary nature of the problems and emphasized also multidisciplinary partnerships to address these problems together. So you can still look at the website that is given here. Now, it was said already a few times today, UNESCO has an agenda for sustainable development. It was developed in 2015 or published in 2015, a shared plan of action for people, the planet, and the 17 sustainable development goals are goals to stimulate action over the period 2015-2030. And these are familiar picture that we've seen a few times already today. Now, mathematics has produced a booklet last year, Mathematics for Action, also under the auspices of UNESCO, where we explain what mathematics can do for sustainable development and for reaching these goals that are formulated by UNESCO. Yeah, so it's in fact a toolkit that focuses on some engaging stories of mathematics in action for sustainable development. It's written by mathematicians, also by thought leaders from across the globe, and it presents fascinating research of how mathematics is addressing the world's challenges. And the toolkit also gives insightful information for decision makers, so they could actually look at this booklet and make decisions based on what is said in this toolkit. Some examples from the booklet on goal number 1, which is end poverty in all forms everywhere. Well, visualizing poverty, that's very important. And in this story about visualizing poverty, it is detailed how mathematical techniques for collecting and mapping poverty data can be used and be more accurate so that action can be taken more easily and based on better data. Goal 6 is about ensuring availability and sustainable management of water and sanitation for all. And there are a few stories here. One of the stories is about managing water resources. That story highlights how a statistical tool, Bayes' theorem, can be used to quantify risks and identify appropriate options for the management of water supplies. There's another story in this section. It's about shifting lake turbidity. That's also a problem, and it highlights how mathematics can provide insights into the mechanism that drive shallow lakes from clear to turbid and support effective, cost-efficient approaches to restore clarity of these lakes. Then goal 11, that's the goal, making cities and human settlements inclusive, safe, resilient, and sustainable. Here is a story, Preparing for a Crisis, which deals with the resilience of digitized systems and also describes some of the mathematical methods and tools that have proven invaluable for addressing vulnerabilities in critical systems. Yeah, so that's the contribution in goal 11. I mentioned already the forecasting of cyclones, and that's a very important topic also, the mathematics of tropical cyclone prediction. It's much better nowadays. They are amongst the biggest threats. They're in the news a lot of times in various places in the world. And what mathematics can do is to lead to improved track and intensity predictions. Early warnings, etc. So improvements in tropical cyclone track forecasting are very important and have been very significant over the last few years, arising from improved observations and models, and also better integration of these through data assimilation. And the accurate forecasts of tropical cyclone intensity remain challenging, so mathematical understanding of the physical mechanisms is important. We have to work on that, and also improving real-time intensity predictions. So how it works is we have some input variables, data that are being observed from various sources. This leads to a number of different models, dynamical models based on mathematical equations, but also statistical models and numerical models, so that's discretizations of the dynamical models. And that all then leads to the forecasts of the cyclone track, of the intensity of the cyclone, and also of the storm surge and the rainfall that are associated with the cyclone. And well, it has improved a lot. Yeah? Tropical cyclone tracking models have improved steadily in the last half century, and the 2019 5-day forecast was better than the 1976 36-hour forecast. So this is really a big improvement. And forecast accuracy on extended time frame has also improved. So today a tropical cyclone track can be predicted up to a week in advance, giving cities the time needed to do evacuations safely. And this really is due to the improved mathematical models that are being used, and also, of course, to the revolutionary data assimilation methods that need to be used. Also in forest management systems, the mathematicians are active. This is a company in Finland where they help in forest management decisions. And important here, I mean, they are active all over the world, and they promote responsible forestry by creating digital twins of forest ecosystems. So, and they are very experienced and have nice mathematical models to be able to do this. And the main mathematical ingredients, as you can see, are Bayesian modeling and machine learning. Also in wind parks, also important, and you see them more often nowadays for the energy transition. This is Horns Rev in Denmark, which is the world's largest offshore wind farm. And well, this is a very nice picture. You see that the water vapor condenses at the tips of the front row and of the turbines, and you see the structure of the turbulent flow through the wind farm. So the ones in the front are actually influencing what is happening behind them. So no offshore wind energy without mathematics, I would say. Also in electricity systems, that's also important. I mean, the energy transition, we go to solar energy, we go to wind energy, but it was shown by researchers from the Netherlands how large fluctuations in solar and wind energy combined with the physical network dynamics of electricity, can cause failures in power grids. And here you see a picture of the grid in Germany. Yellow is wind and solar parks, and blue and yellow are the wind and solar parks. And you see some red tracks where these are very vulnerable for failures. And a mathematical framework developed by these researchers helps to predict the appearance of the potential power line failures. Okay, then on a different topic, the internet and simulations. I mean, many simulations are being done. The internet already accounts for approximately 3 to 5% of global energy consumption, and it's unknown how much simulations cost in terms of global energy. Yeah? It's clear that we should be extremely careful in just bluntly doing simulations. We have to think before we compute. Yeah, so and here is an example from an astrophysicist, and he wrote an article on the ecological impact of high-performance computing in astrophysics. I mean, astrophysicists, they like to calculate a lot. But here you see what the results are of these astrophysical simulations in terms of CO2 production. And you see that these the most popular astrophysics software programs generate quite a lot of CO2. And what's also interesting, that's also in the paper, is what programming language people use. Yeah, I mean, you see some people. I mean, Fortran is of course a very old language, and people are laughing about people using Fortran. But you see that Fortran generates much less CO2 than, for example, Python does. Yeah, so this is also an interesting observation, I think. And yeah, I mean, so curse of size is also, I mean, we want to do bigger and bigger simulations, many more unknowns, and here you see what's happening when you do bigger and bigger simulations. Yeah, so, I mean, initially, like the second column, 2 weeks of blowing and drying your hair, well, that's acceptable, I think, but in the last column, 100 years of world electricity production, that's outrageous, of course. You cannot do that. So we have to think carefully. And this is all associated also with high-performance computing. Chips nowadays don't become faster, so we have to use machines with many cores, many processors, mixtures of CPUs and GPUs, and that implies that the mathematical methods need to be scalable. Yeah, and avoid too much communication between the processors. And that leads to, well, big challenges for mathematicians. And, well, mathematics can reduce the demand significantly. And one of the ways to do that is model load reduction, which is my field. I usually explain it by showing these rabbits. You see that this is a rabbit, but we use only a few facets to display it. We don't need the more detailed picture on the left. Yeah, so that's the essence of model load reduction. Get rid of superfluous detail and only calculate what is necessary. And you can see it here. I mean, this is in red. You see the compute times of available software, commercial software. And in blue, what we can do with model load reduction, and you see that it is much, much, much faster. Okay, mathematics in the HPC era, many challenges for mathematics and urgent need for novel methods, so that's something we should work on. And there was also a report here on exascale computing and what mathematics could contribute to that. Finally, artificial intelligence. We hear a lot in the news about algorithms and artificial neural networks, for example. But the news is really increasingly bad. Yeah? For the tax office characterizing mainly foreigners, TB frauds, and also Google had to withdraw a few months ago Gemini's AI image generator because of anti-white bias. So we have to be careful. Yeah? The artificial neural networks may lead to erroneous results. And, well, we believe that we should equip the neural networks with known properties, yeah? Physical laws to make them reliable. And that's why I always say that we need real intelligence to make artificial intelligence work. And you can think real intelligence, it's more than only mathematics, but certainly also mathematics. Okay, conclusion. We live in the era of mathematics. Its influence permeates economic and social activity. Influence and impact are profound. And the UNESCO Agenda for Sustainable Development can greatly benefit from mathematics to achieve its goals. And we should take care of abundant use of the internet and think before we start to compute, make use of the mathematical toolkit that was presented for the UNESCO. And we can do much better by investing more strongly in mathematics. Yeah, so that's it, as far as I'm concerned. Thank you. Which one?
Slide which tells competitiveness of countries according to mathematical, I don't know exactly, for this reason I am asking you. You have several countries, maybe you have to go backwards, please.
Yeah, I had to wait for the... That was with the booklet, one of the things of the booklet?
No, there is a map of countries, Hong Kong and... No, no? Before?
Oh, yes, I see what you mean.
I think I have not dreamed it.
Yes. This one.
Okay, yes.
Yes.
So could you tell us what's the model used to have the relation between mathematical ability and country competitiveness, because it's very interesting.
I mean, this was an observation that we made. We had Deloitte, the accountants company, make a report for us on the economic value of mathematics. And one of the graphs in there is this one. And what they show is that, I mean, the PISA score on the horizontal axis is the mathematical ability of students that are 15 years of age. And yeah, they plot this against the country competitiveness, and you see really a strong correlation between these two things. Yeah? So it does mean for governments that they should be careful about. And in our country, in the Netherlands, for example, the PISA score is going down in recent years, last 10, 15 years. So there should be a message to the government, hey guys, be careful, because this is going to influence the competitiveness of our country. That's the message we wanted to give.
Is there any estimate of the energy consumption of quantum computing compared to standard computing?
Oh, that's a difficult. I'm not an expert in this. I don't know, but yeah. Well, what I do know is, for example, that ChatGPT, for example, is going to really affect us as well, energy consumption-wise. I mean, but no, quantum computing. Sorry, I don't know. Yeah.
All right. Yeah, we take the last question.
Thank you very much for your outstanding presentation, because you gave us as mathematics an enabler, but you said that is an enabler today. Without mathematics, there are no revolution, no science since the beginning. So we need mathematics to back up and to ground all our developments as far as science is concerned.
Mm-hmm.
And so I'm quite astonished, because you did never mention the education sustainability goals of the United Nations. Why?
Oh, yes, I had to, of course. I mean, the presentation was short, and I mean, I cannot mention everything, yeah, but of course, that's also very important, yeah, that's true. And it's also in the booklet, yeah, I mean, so you will find it in the booklet that I showed, yeah.
Thank you very much, Will, for this very nice and stimulating discussion. And we move to the last presentation. Yeah. It's going to be delivered by Professor Rui Vilela Mendes from CMAF and the Lisbon Academy of Sciences. And the talk is on sustainability and governability, another very hot topic. Thank you.
Okay. Okay, I'll be speaking about some mathematical models of human evolution, and because I don't have time to give the details of the models, if you want to learn about, I have a review paper on my webpage that you can read. The idea is that some very simple models of human evolution lead to some behavior pattern of the Homo sapiens, which might be a block to the achievement of these development goals, which was mentioned already by Professor Duarte. But first, let me see what is sustainability. There is this definition, which is this meeting the needs of the present without compromising the ability of future generations to meet their own needs. So the first question is, what are the needs of the present? And the needs of the present might be the development goals. And so we should ask whether these development goals that were defined as on 2015 to be achieved by 2030, if they are going to be achieved, if there is any progress. We could ask that question, right? Is the first question. Now, and the answer is no. There is no evolution, no visible evolution on these goals. So the needs of the present are not being achieved. And let me show you some examples. Zero hunger. In 2015, the percentage of the population that was undernourished was 7.9. Now it is 9.2. It's worse. Well, now it's even worse, but in 2022, it was worse than in 2015. Another example, the reduced inequalities. There is this index called Gini index, which I'm not going to, I think everybody knows what it is. And the idea is that between 2015 and 2022, at least, it was stable. So there was no reduction of inequalities, in fact. And the situation now is similar. I think of last paper I wrote, I saw recently, I think it is becoming worse, in fact. It was stable. Now, goal number 13, climate action. This is a very important goal, because from this goal depend many other goals, as you know. And so, two examples. The mean atmospheric concentration of carbon dioxide in 2015 was 402 ppm. In 2024 is 422. Got worse. And the annual emissions of CO2 in 2015 was 35.7, and now is 37 something. 37.5. I cannot see it. Okay, so it's getting worse also. Goal number 16, which is peace, justice, and strong institutions. And in usual, you divide this goal in two parts, is the conflicts and justice and strong institutions. Now, for armed conflicts, the number of people that died in these armed conflicts in 2015 was 100,000, say. Now, in 2022 was 200,000. Much worse, double. Okay. Now, what about justice and strong institutions? Here, people that writes about that, they divide in two types of behavior. The first is participation of citizens on the rule of the country. And the second is the application of the rule of law in each country. And now you see that if you go around the world, situation between 2015 and 2022 is worse, become worse, not better. Except in Saudi Arabia and China, where the degree of participation is stable at 0. So otherwise become worse. Okay, so in conclusion, if not even the needs of the present are met, how could one expect any consideration for the needs of the future? That's a very serious, and this is a very serious question, because not to compromise the needs of the future, what we better do is to solve the needs of the present. And why is that so? Why things are not improving? And there are many opinions, and the majority opinions are or that these goals are just nonsense ideas. So do-gooder ideas that are incompatible with human nature. This is the first type of explanation. The second is that there is nobody to enforce them. That is the second question. They are both true, probably. But we'll concentrate on the first one. Are these fulfillment of the needs of present incompatible with human nature? There are authors that think so, and we heard something about today already by Professor Duarte Santos that spoke a bit about that. There are many other papers that say that we are in bad trouble because it's all these good ideas are incompatible with human nature. And now, the work I have done some years ago, and many and other economists did, was to study mathematical models of human evolution, but simple models of behavior of human evolution. And why simple models? Because there are many models of evolution, very complex ones. But simple models have the good point about it because they are very robust. If you take some conclusion, it's robust. So the models I'm going to speak about are very simple models with two agents or three agents. And these agents are not people, are behavior of people. So each one of the individuals might be a mixture of these behaviors. And essentially, the agents in these models are cooperators, free riders, and authorities. Authorities are people that impose rules. And, okay, and there are many papers about that. I would mention some authors, Bowles, Ginty, Choi, myself, Aguirre. So this is a kind of a review on the paper that I mentioned, a kind of a review of all these models. Now, first, cooperation. Cooperation is basic because, as some authors say, that humans are the most cooperative species on the planet. I think that you can agree because they do together fantastic things and very bad things also, like genocide is a cooperative effect also. And so they are a very cooperative species. And now, how it was possible to develop this kind of cooperation trait. And the first result of the models, containing in the models basically cooperators and free riders, is that cooperation is very fragile. So it's improbable to have cooperation. The most, unless you have a fine-tuning of parameters, the outcome of the models is a treasure of the commons. So free riders take over, and then there is extinction or poverty or something. So there is fragility, a great fragility of cooperation. When these models are on isolated groups. But now, if you have groups in competition, then cooperation is stable. So that means that in a sense, like Bowles, it's not my sentence, it's the sentence of Bowles, that say cooperation and war are born to the world at the same time. So cooperation needs conflict. It was born out of conflict. Now, you could think, well, but now we have a civilization, you can change all these traits and so on. However, notice that these studies are referred to the late Pleistocene, which means that we are speaking about a period of 7,000 years. 70,000 years. And that means that maybe some of these patterns of behavior are genetically coded on the organization of the brain. And there are experiments that show that it's true, that this pattern of behavior that I'm going to speak about, they are already consistent with the organization of our brain. And these are experiments done with children, experiments done with measuring the activity of the brain during experimental games, and so that maybe culture has an effect, but some of these pattern of behaviors are already genetically coded. Okay, so the first ingredient that coming from this connection between conflict and cooperation is that cooperation is not general cooperation, it's parochial cooperation. It's cooperation inside a group. Some extreme sociologists say that define parochial cooperation like to love everybody in the group, to hate everybody else. And this parochial cooperation depends on these conflicts, so it's internal cooperation. So parochial cooperation and conflict are two pillars of this, what I call this behavior pattern. The other one is growth, because this is almost a consequence of this pattern. So I would propose that parochial cooperation, conflict and growth is the behavior pattern of Homo sapiens, and in a sense is a kind of genetic, evolutionary heritage of Homo sapiens. Okay, is that good? Is that bad? And what I want to speak about now is that this pattern of behavior, each one of these pillars, has as a result a crisis, a problem. So parochial cooperation needs, this was an image of this parochial cooperation and growth, but not important. It was generated by the LLMs, by an LLM. I don't like to call the artificial intelligence, because it's not artificial intelligence. It's a large language model based on pictures. Okay, so, so the crises that are born from this behavior pattern. Well, first, you know that you need conflict to maintain, to generate cooperation. But if there are no conflict, you need to maintain cooperation. Otherwise, that becomes unstable. So, what human society invented many long ago, even in the Pleistocene, was an authority. So, another agent appears, another agent in the model, which is the authority, the one that implements the rules, that maintains cooperation stable even without conflict. And that generates, and if you look at the world around you, it generates another tragedy. I spoke about the tragedy of the commons, by the dominance of free riders, and now if the authorities, instead of doing what they are supposed to do, which is to maintain cooperation in favor of the group, if they use their power to do other things or to not to fulfill their role, that in the models we call it a tragedy of authorities. It's when authorities just take the power. And you see around the world many examples of the tragedy of authorities. Some of them are autocratic government, others are excess of bureaucracy and so on. In many places, even in local government, you see many examples of tragedy of authorities. You can see in the papers some examples. Now, the second pillar of the behavior pattern is conflict. And conflict in the past was not, well, was bad, many people died and so on, but was not serious. But now conflict is very serious, because a conflict may become an extinction event. So another crisis comes for a general conflict, or a local conflict that generates a global conflict. In the past, these conflicts, even large wars, did not destroy human civilization. But now, a large conflict might destroy human civilization. So conflict itself might generate an extinction event. And now the third crisis comes from growth. Because growth was good. Was good in the past where you had plenty of room to expand. But now humankind is colliding with the boundaries in many ways. Everybody speaks about the climate, but it's not only the climate, it's the materials, is the collision that we have with other species. We are causing extinction of many species because of our growth. So there are three different crises. And okay. Too fast. Now, what should we do? That's this question. What should we do? Well, the nice idea that would be to have a new cultural paradigm that everybody speaks about, which is another do-gooder idea, because that would be cooperation within a single group, the whole human planet cooperating with itself for all these things. That would be possible. Probably it will take the same time of evolution that the previous behavior pattern took. So it's not very... Can we wait that long? Can we wait all this time? And another idea which I think has more success is that we should have control by a central government. And you see that there was no success at all. Let's see the example of conflict regulation. You see, you create a League of Nations and then the United Nations to make a regulation of conflict. And conflict was never regulated. Why was that so? Because the creation itself of the United Nations League of Nations goes against one of the pillars. Because it's like people, the very well-intentioned people that created this, they want a world government. But the first pillar of this pattern of behavior is that peak operation, and peak operation is nationality. And her world government goes against this idea of nationality. So in a sense, I think the United Nations, it's very serious to say that, but I think it's a matter of casting. Should not be constructed that way. Now, what should we do? And the conclusion, in the paper I have some ideas, some suggestions, which I won't want to detail, but the only message I want you to take home is that any measure that you devise to deal with the crisis should not confront these pillars, should try to go around these pillars. For example, suppose that the fulfillment of these goals should not be done by a kind of world government, not even like with the United Nations, should be a kind of coalition of the people that is concerned, and just for that particular goal, not as a general rule for the world, and so on. There are many ideas for many authors about that. But in any case, if you don't want to wait all these years of evolution again to change the paradigm, you need to think about it. Otherwise, if you don't do something, we'll have a bloody mess, and which already is the state of the world these days. And but in any case, we are free to change the world. I'm not anything.
Is there any comment or question? Well, it's rather late. For sure. Yeah, good. And of course you invited us to think about this, which is very important. So thank you very much again, and this is the end of the section of today. Thank you.